What I showed you last time was a very simple model that we're going to use to model reading times or reaction times, in this case of a button pressing task. And so the model looks roughly like this. We've got, for each of the n data points, we are assuming that the data are coming from a normal distribution with some mean mu and some standard deviation sigma. Right? So this is a very simple linear model that one could fit to this kind of data, right? You must have seen this kind of model. If you've done any kind of linear modeling, you might have seen this statement written like this, so that the reading times are a function of some intercept and there's some residual noise, where the residual noise comes from a normal distribution with mean 0 and standard deviation sigma. These two things are the same model, okay? They're just two ways of writing the same model, and it is common to write that the residual errors are independent and identically distributed. That's an assumption of the linear model, the simple linear model, okay? So, well, what does this model actually assume? Well, first of all, it assumes that the data are coming from a normal distribution. It also assumes that there is some unknown parameter mu and some unknown parameter sigma, right? That sigma is going to represent the noise in this process, the amount of variability around that mean value mu, but these are the two unknown parameters, in this model, right? And of course, we are assuming that the noise, this residual term here, is normally distributed with mean 0. That means that there is some mean mu and there is some Gaussian noise around that. That's what this model is, okay? So if I were fitting a standard frequentist model in R, how would I do that? I would use the LM function. I would have RT as the dependent variable, and 1 here is the intercept, right? That in the linear modeling framework, that's the estimate for mu that I will get, and this is the data frame that I'm using, right? And so if I fit this model and I look at the output of this model, just focusing on the coefficients, the intercept that I get from the model, I get a mean of 168 milliseconds, right? Approximately, and the residual error in this model is about 24 milliseconds. And as you should notice here, these two numbers, they are just the maximum likelihood estimates from the data, right? I could have just calculated the mean of this vector of reading times and I would get exactly the same number as the intercept. That's what the intercept means, right? It's telling you the mean value from the data, and the standard deviation I could have computed by hand by just computing ST here, right? So you see that these two numbers are exactly the same. So basically the linear model is delivering you two maximum likelihood estimates, one for the intercept for mu, that is mu hat, and it's giving you an estimate of sigma hat as well, the estimate sigma hat as well, right? So these are estimates of the two parameters in this model, right? Very simple. Now in the Bayesian world, we don't just have the maximum likelihood estimates. We are going to be using we're going to define priors on the mu and the sigma parameters, right? Because for us, as Bayesians, these are not unknown point values out there in nature. These have prior distributions on them, right? Even the parameters in a Bayesian framework will have a probability density function associated with it. That's the prior distribution, right? Okay, so this is in stark contrast to the frequentist approach, okay? I just want to stress this again, that where mu and sigma in the frequentist modeling approach would be unknown fixed values out there in nature. This is a very big departure from that assumption, okay? And this has far-reaching implications for data analysis, as I will show you later. So what does this model look like now in the Bayesian framework? In the Bayesian framework, you're going to have to define a prior for each parameter. Okay, so for mu, I've decided that I'm going to take a very interesting prior. Okay, so this prior is a uniform prior. That means it assumes that every value between 0 millisecond and 60,000 milliseconds, so 60 seconds, okay, they are all equally probable, equal likelihood. Okay, and for sigma, I'm going to assume that all values between 0 and 2000 milliseconds are equally likely, right? So I've just chosen these two priors as a starting point. So later on, we are going to elaborate on this model and choose some alternative priors, which perhaps make more sense. But this is a good starting point just to illustrate how the machinery is going to work, okay? How the computational machinery will work now. And I also want to point out now that I don't need to worry about whether I have a conjugate prior for the likelihood I'm working with. I can choose whatever prior is reasonable for me, right, which makes sense to me. and the computational tools will allow us to get samples from the posterior. This is why we can go far beyond the conjugate cases, the simple conjugate cases that we had earlier. Okay, so let's think about what these priors imply. Okay, the model that we are going to fit with the software package BRMS. So there's a package called BRMS that you must have loaded when you started this course, installed when you started this course. In that package, there's a function called BRM, which has the same syntax as the LM function that I showed you earlier. Okay, the only difference is that there's a few more details that are added in this functionality, in this function here, right? So we've got RT as a function of the intercept. That's just like the linear model. Here's the data specification. One important thing that is added in the BRM function is the family. So what this statement, this family Gaussian is saying is that the likelihood that we are assuming for the data is the normal likelihood. A synonym for the normal likelihood is the Gaussian likelihood. So that's why we have Gaussian here. Okay. One other new thing in this function which is not there in LM obviously is the prior specification. So you see that there's a parameter called prior, and I'm going to give a list to this parameter, and this list gives you the opportunity to define a prior for the mu parameter, which is the intercept, and a prior for the sigma parameter. Okay, so these are the two parameters in this model, right? And notice that I'm giving the form of the prior distribution going from 0 to 60,000 milliseconds, and I also explicitly define lower and upper bounds with this LB and UB function. This is needed to prevent the sampler from accidentally sampling from outside that range. Okay, it's just a technical detail. Right now you don't need to worry about it, but you have to include this when you're defining these kinds of these priors that have limits, on them, right? So for sigma, I'm assuming a 0-20,000 prior uniform, right? And again, I define these bounds here. So this is the new part here, right? This is one new part. Another new part is this part here, which I'll just quickly explain. So I've explained all these things here. So let's focus our mind on this part of the output where we've got, or the input, sorry, where you have to define chains, how many chains you have. So the default in BRMS is 4, and you have to also define how many iterations you're going to have. The default is 2000, and you also have to define what the warm-up is going to be, and that is the default value is 1000. Okay, so you could actually leave out in this command, you could actually drop this entire 3 terms here because these are the default values anyway. But let me quickly explain what these things are doing, right? So when I run this model, when I fit this BRM model, right, I will get an object that returns the posterior distributions for the 2 parameters, right? Samples of the posterior distributions from the two parameters, right? And so the chains that we are getting from in the output, these are essentially 4 sets of samples, 4 sets of independent samples for each parameter. Like for the intercept, for the mu parameter, I have 4 independent vectors of samples. And the reason we have multiple chains, right, multiple samples, sets of samples, is that we want to check that we are consistently getting samples from the same distribution, right? So we want to look for consistency through these chains. That's why there are 4 chains by default in BRMS, and you should leave it at that. You should not change that for these kinds of simple models, right? Iterations refers to the number of samples you're going to collect, right? So 2000 samples is what we will collect, and warm-up refers to the fact that in the beginning, when the sampler starts to obtain samples from a particular parameter, in the beginning, it's lost in the real number space. It doesn't know where the samples should be coming from, and that initial period is called the warm-up period. The sampler is quickly approaching the true posterior distribution given the data and the prior, and so what we do is we generally throw away the warm-up period and just don't look at that, because that's when the sampler is just starting to look for the posterior distribution samples, right? So in other software packages, historically there used to be these other packages that people sometimes still use, you've got the WinBugs package and the JAGS package. There the warm-up is called burn-in, okay? It's just the same thing, right? So what you should do is maybe read a little bit. There's a small section in chapter 3 in our textbook on this, on sampling and convergence, where we talk a bit more about these things. So what you get as a result of the model fit, okay, so is a graphical summary here. We are seeing the posterior distribution of the mu parameter, right, and the posterior distribution of the sigma parameter. On the right hand side, you're seeing the chains that represent the 1,000 samples. Having thrown away the initial warm-up 1,000, we are left with 1,000 samples from each chain. So total of 4,000 samples. If we sum up all the data, all the samples from these 4 chains, we are getting a visual graphic of how the sampler was searching in the posterior distribution. So what this shows is that the posterior distribution, most of the samples are coming from this range here, and occasionally there are some rare samples from 172 and 166 and so on, right? So this kind of plot is called a caterpillar plot, and what this is showing you is that the chains are sitting on top of each other, right? And so what we say in Bayesian statistics is that this plot is a fat, hairy caterpillar, right? So when you get a fat, hairy caterpillar, that means that all the chains are consistently sampling from the same distribution, and so this is a good situation to be in. Later on in the textbook, you will see some pathological cases where you do not see these kinds of fat, hairy caterpillars. One of the chains is going off in one direction, the other chain is going off in another direction, unable to sample from the posterior consistently. So that is a bad situation, and that's called a convergence failure. And you can read more about that later, but right now we are looking at pretty simple models. So we're not going to hit any convergence problems anyway. So let's just focus on the posterior distribution, what we can learn from it. Okay. So one thing you should try at home now is to install this ShinyStan library, and then just type launch ShinyStan after fitting this model, and then look at what happens. You're going to have an interesting time looking at the posterior distributions and other statistics in the model, right? So it's a very useful exercise. Just try it out. Okay. All right, so what is this model that we just fit? We can also extract the posterior distributions as vectors, right? So here's the vector for the sigma, for the intercept, and here's the one for the sigma. These two I will ignore right now. We don't need to worry about this right now, okay? And so what I can do is I can extract from the posterior for the mu parameter, the intercept parameter, I can compute the mean, and I can compute the 95% credible interval, right? That's what I've done here, right? So this would be what I would report in a paper if I was doing this as an analysis to publish somewhere, right? I would report the mean and the 95% credible interval. This tells me pretty much everything I need to know about this parameter, right? After I've seen the data. And I could do the same thing for sigma, right? So here's sigma. So I've computed the mean and the 95% credible interval of this. So the end result of this analysis is that I know, having seen the data and given some priors that I chose, I know what the uncertainty is on the parameters that I have in the model, and I can draw my inferences from that. Okay. So the next thing I will discuss now, two very important concepts. The first is looking at prior predictive distributions, and the second is posterior predictive distributions. So these will come up in the next lectures.